In this problem, we're going to go ahead and solve problem number 47, which is from chapter 4 in the textbook. This problem, the data is from the number of cases of COVID-19 in the United States from the start of 2020. We have all the data here, and we want to use technology to create a scatter plot for it. We're going to use Desmos in this case. The advantages of Desmos is I can actually copy this data on Control C or Command C, depending on if you're Mac or PC. I can come over here to Desmos, and if I just hit Command C or Control C, I'm sorry, Command V or Control V, it will actually put that data right into here. It also nicely sets my window based on this data. And I can now see my graph where it comes along, it goes up, and then it kind of starts to level off. So there's my graph. If I would like to plot this or copy this, I can actually click on this button that says Share Graph and export the image. At this point, I would like to answer some other questions. I'd like to use technology to create an appropriate model for the number of cases based on the month. So this looks like a logistic graph. So what I need to do is know what does a logistic graph look like. So I'm going to go through the textbook until I find the logistic graphs, see kind of what they look like, that logistic function. So I'm going to have to come back up here a little bit farther up and get to what it looks like. And what I would do for all of these problems is look through to see what those graphs look like, find out what those equations are looking like. So we have all of them listed in here at the start of the modeling of what the different graphs would look like. So this one is M1 over 1 plus K e to the minus CT. So first thing I notice is my variables are X1 and Y1. Y1 is my dependent variable or output variable. So I'm going to type a Y. If I type a 1, it'll automatically make it into a subscript. I then need to do a tilde. Because I don't want to do an equals, the tilde is what tells Desmos, hey, this is where I want you to kind of come up with the equation. I then may type this exactly as I see it. I see M divided by, notice it put it in the denominator, 1 plus K times E to the negative C times. Now I can't use T, because if I use T, it's not my variable. My variable for my input is X1. So I'm going to type an X and then a 1 to make it a subscript. Notice once I do that, it actually draws that graph directly on my graph, on my graph. So that line is now on there. I can see how well it fits my data. All right, so it fits pretty good. I can now see what is my parameters. My parameters are again the M, the K, and the C. So I now can see what those values are. If I want to, I can now come back to my problem. And you can actually, if you want to, type this in. I mean, you don't need to type it in if you don't want to, but it would be helpful just to have that equation down or write it down somewhere. So here the Y is equal to M. My M parameter is 3.7756 times. Now the times on Desmos is the star, which is above the 8 key, and times 10 to the 7th. That's scientific notation, so it's just a really big number. So the 2 that was the caret, which is above the number 6. And then we're going to divide that by, and this time I need to use parentheses because I don't have a way to write fractions on a computer. If you were writing this by hand, you can certainly write it in the denominator. Then 1 plus my K parameter is the 234.7, let's say. And then I've got times E. And again, I want to raise that to the negative C, which my C is 0.492, let's say. I don't need all the decimal places. So I won't write them all. And then times X. X being my variable. And there's my model that models this information. I also want the R squared value. right here, it gives me an R-squared value. It tells me it's 0.9907. So I now have my R-squared value. Another advantage of the calculator is I can get that R-squared value. So 0.9907, and that means, to interpret it, it means that 99.1, let's say, % of the variability in the number of cases is explained by the model. So that's pretty good. That's pretty high up there. That's a pretty good percentage. They're not always this high. This one just happens to be pretty good. I then want to use my model to estimate the number of cases. You can do this several different ways. You can just type this into your calculator. You can type this into Desmos. I can actually copy and paste it into Desmos. Notice it actually puts it into Desmos. The only thing that kind of messes up is it doesn't do well with the powers here, so I have to type that in. Oops, can't type it in correctly. And then I do want to multiply that by, and unfortunately, it doesn't seem to do the multiplication correctly either. So I'm going to go ahead and put it up here right before the negative sign, or even right before the negative sign. I'm going to type in, I want to do it for 18 months. So 18 times that negative sign. And I now can see what that that value is. So that's how many cases there were in that year. So I now know in the year 18 months after the start of 2020, there were that many cases. And I probably would round that off because we can't have partial cases. So that's how many cases there are. The question is, should it be trusted? Well, 18 months is outside the original data. So I really probably shouldn't trust it. I don't know necessarily what's happening at that point. There are things that could have happened. There could have been more cases. There could have been less cases. There could have been a new variant. So really shouldn't trust it because it's outside of what my original data was I collected. It wants me to now do the same thing for 24 months. So all I got to do is come up into my formula here, change my 18 to 24. And I'll find out how many cases there were in 24 months into the pandemic. And again, that number probably shouldn't be trusted. I should also round it off probably to 5. And it shouldn't be trusted because it is outside the original data.